So we informally defined in a way the remainder theorem. But let us go back and let us formally define the remainder theorem, and from then we can clearly understand this whole thing again, and then we'll extend our definition to the factor theorem. So here I would like to write that the function values at x equals -1. So in particular we are talking about this example and this example, and x equals 2 are same as the remainders. And that's the informal definition for a remainder theorem, that the function values at these points, at these -1 and 2, they also give us the remainders. So now, if you ask what is the purpose of using this remainder theorem, well, the purpose would be we already have one method to find the remainder, which is the synthetic division. Now we also have another method to find the remainders. So we have two methods. We can verify if we are not sure that this is correct, we can verify it by using the second method. So in short, we have two methods, and at times this might be more convenient, at times this might be more convenient. And we'll see examples where this might be more convenient. Okay. So let us formally define the remainder theorem. Okay. So the formal definition for a remainder theorem is, and for that I will use this space here because we are already done, and we have these the relationships right here. So we can formally write the remainder theorem. So the remainder theorem says when we divide a polynomial f of x, look at this example, f of x could be any polynomial. Here we have x cubes, then we have again cubic. So it says when we divide a polynomial f of x by a binomial of the form x minus c. So that's why I said we want to confine ourselves to x minus c for now. Then the remainder is f of c. So this is what we have here. The remainder is the value of this function at point c, at number c. So here we have c is -1, so f of -1 gives us the remainder. For this case we have c is 2, so g of 2 gives us 11, which is the remainder, and we verified that in these two examples. So this is this a coincidence that it works only for these two cases? No, it's not a coincidence. This works perfectly fine for all different values of c, as long as we have this scenario where we have a polynomial function and we are dividing by a binomial of this form. Okay, so let us quickly convince ourselves that it really works for all the c's, because it's easy to say that okay, it works for these two examples, so from that we can conclude it works for all. Mathematically that is not correct. We have to kind of verify it or prove it for all different values of c. So in order to do that, what do we need to do? So what we need to do here is we want to start writing with the general form, the most general form, and from there, in one or two steps, we would be able to conclude that this holds, the remainder theorem holds for all the values of c. How would we do that? Let us first start writing the general form. And the general form is that the dividend, all the time we are relying on our nice old friend that we already know from our elementary school, the relationship. Dividend equals divisor times quotient plus remainder. So in general we can write f of x is our dividend. That equals the divisor. What is the divisor? X minus c. That is our general divisor. So x minus c times the quotient. So let us represent the quotient by q of x. So q of x could take any value. It can be a quadratic, cubic, depending on what we start from with the original function. And then of course there is the final piece, which is the remainder r, right? And we are trying to verify it for any c. Okay, we are trying to verify this for any c. What does that mean? What did we do here? We tried to evaluate this function at -1 and 2. That was the c value for the first case and the second case. But in general, we are talking about any c. So which means we want to evaluate this function when x equals c. So we substitute x by c. If we do that on the right hand side, we will also have to replace x by c. What happens here? We have c minus c, then q of c plus the remainder r. But if you look at the right hand side, we have c minus c. But c minus c is simply 0, and 0 times any other quantity is also going to be 0. So this term kind of disappears, or is simply 0. And then we have 0 plus r, which is going to be just r. So we can write f of c, which means f evaluated at c equals simply r. And the other way to write the same thing would be, so which means this is equivalent, so this is a sign for equivalence. So we can write the remainder r equals f evaluated at point c. And that is what we wanted to prove. That the remainder obtained by dividing a polynomial function by any binomial of this form is f of c. So now we can say with confidence that this is going to work for any value of c for this scenario. Okay? So that is our remainder theorem. This is the formal way to write the remainder theorem, and this is like a mathematical way to prove the remainder theorem. Okay, so we're done with the remainder theorem. We have successfully used the synthetic division, and we can use the remainder theorem as well to find the remainder. Now for the final piece, the factor theorem, let us go back to our original number system. And let me ask you a different question now. We started with finding the remainder. Now let us ask ourselves a different question. So we are about to answer our final goal for today, which is to find whether this particular binomial is a factor. So now let us ask ourselves whether is 4, so I'm just rewording it. So is 4 a factor of 15? That's our first one. And then we have the other one. Is 5 a factor of 25? Well, the answer for the first one is certainly no, it's not a factor. And the answer for the other one is that yes, 5 is a factor of 25. So yes. Now here I want you to carefully look at the remainders. Look at the remainder for the first one and for the second one. In the first one, the remainder is 3, right? And in the second one, the remainder is 0. So what do you observe here? If you look at the remainders, when the remainder is 0, we can justify that the 5 here, the divisor, is a factor of the dividend. In this case, when the remainder is non-zero, it's 3. What do you see? We see that 4 is not a factor of 15. And we could take a few other examples. For example, we can take let us take 18 or 7 a factor of 18. And the answer is no. Because when you divide 18 by 7, you get, let's do that. You have 18 divided by 7. So you have 7 times 2 is 14. What do we get as the remainder is 4. So it's not the factor. How about is 2 a factor of 4? Is 2 a factor of 4? Let us set up the long division. 4 divided by 2. We have 2 times 2 is 4. The remainder is 0. So again, here in this case it is yes. So if we carefully look at the remainders, we would see that when the remainders are 0, like in these two cases, then this number, this divisor is a factor of 25. So 25 can be written as 5 times 5. Same thing with this 4. 4 can be written as 2 times 2. And of course, the number 2 is a factor of 4. 5 is a factor of 25. In that case, the remainders are 0. And in the other two cases, we have a non-zero remainders. The remainder could be positive, like in these two examples, there we have positive remainders. They could be negative. But as long as they are non-zero, these divisors 4 and 7, they are not factors of these 18 and 15 respectively. And the same idea that we observe and see in these numbers can be again extended to the polynomials, and we can figure out whether a given binomial is a factor of a given polynomial. And for that, what do we need to see? In these two cases, in these four cases, what are we looking at? The remainder. The remainder is 0, we say it's a factor. Remainder is non-zero, we say it's not a factor. Now, let us go back to our polynomial equations. We have this polynomial divided by that, and secondly, this other one divided by this binomial. What is the remainder in the first case? In the first case, the remainder is 0. So what can we say about whether x plus 1 is a factor? We would say yes, it is a factor. And what would you say about x minus 2? Since the remainder is 11, we would say that x minus 2 is not a factor. And in words, what we just said is informally again the factor theorem. So let us formally write the factor theorem, and then we'll just combine and conclude combine these results, and finally we'll say the final thing about whether a binomial of this particular kind is a factor of a polynomial. So in order to do that, I will get rid of this, because we already know that the function values give us the remainder. So the factor theorem can be formally written like this. If the remainder f of c equals to 0, and we already know that from the previous work on the remainder theorem that f of c is our remainder, so we can say f of c is the remainder f of c equals to 0, then the binomial x minus c is a factor of the polynomial f of x. And that's what we did observe in all these four examples. And so again, certainly we can see that again from these polynomial equations right here. Okay, but again, the question is still the same. Okay, it works for these four cases. We looked at these four examples. It also works for your polynomial. We can see that from all this work when we write the dividend as a product of the divisor times the quotient plus the remainder. So we can see that from there. But does this work for NEC? Yes, it does work for NEC, but we have to have some kind of mathematical proof to convince ourselves that yes, this does work for NEC. How would we do that? Well, in order to do that, we again have to go back to our general form. Well, we really like our general form. So we'll start with our general form. We have, and this proof is, again, it's as short as we have the proof for remainder theorem. So we have f of x equals, same thing, x minus c times the quotient, divisor times the quotient plus the remainder. So what we are going to do first is, we can replace this remainder by f of c, well, we already know it's the same thing. Value of the function at c is the remainder. So to skip a step, I would replace this r by f of c. Right, we can do that. And then let us go back to the theorem. The theorem says when the remainder is 0, then this binomial is a factor. So which means we want to set this remainder equal to 0, right? So let us set this equal to 0. What do I have? We have f of x equals x minus c times the quotient. And then plus a 0. Well, plus a 0, we don't really have to write it. So we can just simply write that this polynomial function equals to x minus c times the quotient. So here we can very clearly see from this step here that x minus c is in fact a factor of this polynomial f of x. So which means we have proved this for all general cases, which means for all c's in the real number system. Because we are confining ourselves to real numbers and the coefficient of x is 1, and we are dealing with the linear functions. Okay? So to conclude, what did we learn? We learned two important things. The first thing that we learned was how to find the remainder. And in order to find the remainder, again, we will rely on two things. We can rely on the synthetic division for polynomials, and we can also use the remainder theorem by evaluating the function at that particular c. So once we have the remainder, then what is the next important step so that we can say whether a particular binomial is a factor of a polynomial? So then we rely on our factor theorem. So once we find the remainder, if the remainder is 0, then we go back to the factor theorem. Now what do we say? If the remainder is 0, then the particular binomial is a factor of the polynomial. If remainder is not 0, then it's not a factor of the polynomial. So let us formally write it, and then we'll look at a quick example. And then I will give you some practice problems so that you can work on your own. And then for next lecture, we will use these concepts to do something more important. Okay? So let us go back and look at a particular example. And I would like to show you how we would formally write the whole argument of using the factor theorem. So if we have to do something like this, we want to determine whether, so now we're combining everything and we're addressing our main goal. So we want to determine whether x minus 4 is a factor of this polynomial function f of x equals x to the 4th minus 3x plus 5. So what are the steps that we have to do? The first step is we have to find the remainder. How would you find the remainder? Well, we could use the remainder theorem, which means we just substitute x equals 4 and find this expression, simplify this expression, and find the remainder. And from the remainder, then we can go back to the factor theorem and say whether it's a factor or not. Or, if we don't want to use the remainder theorem, then we can go back to our synthetic division method. So in this case, let us use our synthetic division. In order to set up the synthetic division, what do we need? We need the c. This is already in the right form, x minus c form. We have c equals 4. So I will set up the synthetic division 4. And then we have to carefully write the coefficients of the polynomial function. In this case,